In this video, I'm going through the whole topic called rates of reaction, and that's if you're studying AQA Combined Science, also called AQA Trilogy. If you're studying separate science or a different exam board, just check your revision guide in case there's a few extra bits you also need to know. So what does rate of reaction mean? Well, put simply, the rate of a chemical reaction is how fast it's going. So it's how fast the reactants are being changed into the products. In this chemical reaction, we can see it's bubbling and fizzing a lot faster and giving off much more steam, so we can see that one is clearly reacting faster than this reaction. But rather than just saying this reaction is happening quicker, we want to be quantitative. How much quicker is that one reacting, and how fast is it actually reacting overall? When deciding how to measure the speed or rate of a chemical reaction, you have to look at the products that are being made. So this equation here, when we look at the state symbols, tells us that a gas is being made. And there's three different ways of measuring the rate of a reaction when a gas is made. The first method I'm going to show you uses a gas syringe connected to a conical flask via a delivery tube. And I've already got in here some hydrochloric acid. So I'm going to add some magnesium and then very quickly replace the bung, and at the same time start the stopwatch. And what I would do to measure the rate of reaction is every 10 seconds or every 30 seconds, read off the volume of gas that's being produced by the reaction. The second method of measuring the rate of reaction if a gas is produced is to use an upturned measuring cylinder that's already been filled with water, and it's clamped in place with the open end of the cylinder just a centimetre or two off the bottom of this water trough. And that's connected to the conical flask via a delivery tube again, and the delivery tube is inserted just inside the open end of the measuring cylinder. So I'm going to add my second reactant. I've already got some acid in here, I'm adding some magnesium to it, replace the bung, start the stopwatch straight away, and you'll notice that as the gas is being produced, it's bubbling up through the water. So every 10 seconds or every 30 seconds, I can read off how much gas has been produced by looking at the space at the top of the measuring cylinder. Here's another method of measuring the rate of reaction when a gas is produced. I've got some hydrochloric acid in the flask, and we're carrying out the whole reaction on top of a balance. I'm then going to add the second reactant, in this case magnesium, and start the stopwatch. And what we'll see is the mass will start to decrease. As it's losing a gas, those gas molecules escape into the air, so the contents of the flask are going to get lighter. And what we'd have to record is the mass of the flask and all of its contents every 10 seconds or every 30 seconds. You'll notice I've got some cotton wool in the conical flask, and that's doing two jobs for us. First of all, it's stopping any acid spray from coming out of the flask. It's also allowing the gas to escape, so the mass will decrease and we can therefore measure the rate of reaction. Sometimes in a chemical reaction, a solid is made. And if that solid is made by reacting together two liquids or two solutions, we call it a precipitate. And we'll notice that because the solution will start to go cloudy as tiny bits of solid are formed. So to measure the rate of reaction in this case, we use something called the disappearing cross method. In this method, we start off with a cross on a piece of white paper, and we stand our conical flask on top. I've already got my first reactant in there. And when I add my second reactant, I start the stopwatch, give the reactants a quick swirl, and then we're going to time how long it takes to go so cloudy that I can no longer see the cross through the reactants. I'm going to speed up the video a little bit so you can see how it will turn cloudy, and then we'll no longer be able to see the cross. And when it's gone so cloudy that you can't see the cross, we then stop the stopwatch, and that will give us an indication of how fast the reaction has gone. When I drove to school this morning, my car told me at the end of the journey that my mean speed was 25 miles an hour. But I know for a fact I didn't keep a steady 25 miles an hour. There'll be times when I was going slower, there might be times when I was going slightly quicker, and there'd be times when I'd actually stopped. So that was just a mean speed for the whole journey. Chemical reactions are the same. We can work out a mean rate of reaction for the whole reaction, but it doesn't mean it was going that speed the whole way through. So to calculate the mean rate of reaction, we can use one of two formulas. If we're measuring the volume of a gas, for example, we could use the amount of product made divided by time. If we know how much reactants we started off with and we've timed it until they've been used up, we can also use the amount of reactant used up divided by time. Here's an example. What is the mean rate of reaction if 25 centimeters cubed of gas is made in 10 seconds? So for this one, we use mean rate of reaction is the amount of product made divided by time. So it's making 25 centimeters cubed of gas, and the time is 10 seconds. So 25 divided by 10 is going to be 2.5, and the unit will therefore be centimeters cubed slash seconds. So centimeters cubed per second. Here's a different example. What is the mean rate of reaction if 5 grams of magnesium is used up in 20 seconds? So this time we need to use the equation mean rate of reaction is the amount of reactant used up divided by time. So we're using 5 grams of magnesium, and that takes 20 seconds. So 5 divided by 20 is 0.25, and this time the units will be grams slash seconds. So grams per seconds. All we've calculated so far is the overall mean rate of reaction. But for your exam, you also need to be able to calculate the rate of reaction at a specific point in time. So let's look at this question. Calculate the rate of reaction at 20 seconds. So to do this, we need to be able to calculate the gradient of the line above 20 seconds. So the first thing we do is we draw on a tangent of the graph up from 20 seconds. And then we make this into a triangle. And we need to work out the rise of the triangle, so how much it's gone up. It's gone up from 28 centimeters cubed up to 48 centimeters cubed, so that's the difference of 20. And then we need to calculate the run, which is how much it's gone along, and it's gone from 10 to 34, so that's a difference of 24 seconds. So to calculate the rate of reaction, we need to calculate the gradient of that line. So that's going to be the rise divided by the run, which is 20 divided by 24, which is 0.83, and the units are going to be centimeters cubed per second. If you think you need to go over this in more detail, I'll put a link up here now to another video I've made looking at how to do this. As well as calculating the rate of a reaction, you can also use the gradient of a graph to give you an idea of how fast the reaction is going. So if we measured the volume of gas produced, say every 10 seconds using a gas syringe or an upturned measuring cylinder, we'd get, more often than not, a curved shape like this. And if we look at the gradient of that graph at various points, to start with, we'd find that the gradient is steep, and that tells us it's a high rate of reaction. The reaction is going fast at the start. Then partway through the reaction, the gradient wouldn't be as steep. That tells us the reaction is slowing down, or it's a lower rate of reaction. And then finally, where the graph levels off, that tells us that the reaction has finished. So we've run out of the limiting reactant. If instead we carried out the reaction on top of a balance and looked at the changes in mass, we would get a graph something like this. And once again, we'd find that at the start, the gradient is steep, and that means it's a high rate of reaction, or the reaction is going fast at the start. Partway through the reaction, the gradient isn't as steep, so it's a lower rate of reaction, or the reaction is slowing down. And then eventually, the graph would level off when the reaction has finished. So why is it that chemical reactions tend to start off fast and then slow down before they finish? Well, to understand that, we need to look at something called collision theory. For a chemical reaction to happen, the reactant particles must first of all collide with each other, and when they do, they must have enough energy for them to react. The minimum amount of energy that particles need when they collide is called the activation energy. If they've got the activation energy, they will cause a reaction, and we call that a successful collision. If they haven't got enough energy, they will simply bounce off each other without reacting. So how can this explain why chemical reactions start off fast and then slow down before finally stopping? Well, at the start of the reaction, when the chemicals have just been mixed together, there are lots of reactant particles, so there will be a high frequency of collisions and therefore a high rate of reaction. The reaction will be going fast. Halfway through the reaction, some of the reactant particles have been used up, so there are less reactant particles left. So that means there will be less frequent collisions and a lower rate of reaction, so the reaction will be going slower. Eventually, there will be no more particles for one of the reactants, so the reaction will finish. If you're finding the video useful, please could you give it a quick like. Thank you. Now we're going to take a look at the factors that can affect the rate of reaction. In other words, things that can speed up or slow down a chemical reaction. And they will be concentration of reactants or pressure if we're using gases, the temperature of the reactants, the surface area of the reactants, and whether we use a catalyst or not. I'm going to use the disappearing cross method to show you the effect of concentration on the rate of reaction. So I've already measured out 50 centimeters cubed of sodium thiosulfate into each flask, and in each flask the concentration of that is 0.15 moles per dm cubed. So that's a control variable. But what I am changing, my independent variable, is the concentration of the hydrochloric acid. This one that I'm going to pour into here is 0.4 moles per dm cubed, so that's a lower concentration, whereas this one is 1.0 moles per dm cubed, that's a higher concentration. So let's see what happens. I'm going to speed up the video as well so we can see the effects much quicker. So at this point we'd stop the stopwatch on this reaction because we can no longer see the cross. And now the lower concentration has also turned fully cloudy. So what does concentration actually mean in terms of the particles? Well, in a dilute solution or a lower concentration, we've got less particles of the chemical in the same volume of water. And we can see that the reactant particles are less crowded. If we've got a more concentrated solution or a higher concentration, we've got more particles of the chemical in the same volume of water, and therefore the reactant particles are going to be more crowded. This means that concentration of the reactants is going to affect the rate of reaction, because if we've got a dilute solution, the reactant particles will be more spread out, or in other words, there'll be less reactant particles in the same volume, and that means there'll be less frequent collisions and therefore a lower rate of reaction. If we've got more concentrated chemicals, or the concentration is higher, the particles will be more crowded, or in other words, there's more reactant particles in the same volume, and therefore there'll be more frequent collisions and a higher rate of reaction. If we're reacting two gases together, the effect of changing the pressure is similar to changing the concentration when you're dealing with solutions. So the pressure of a gas can be increased by pumping more gas into the same space or by making the space smaller. And we can see when you do that, that means the particles are more crowded, there will be more frequent collisions, and therefore there would be a higher rate of reaction if the pressure is increased. I'm now going to show you how the temperature of the reactants can affect the rate of reaction. So I've already prepared 50 centimeters cubed of hydrochloric acid into each of these flasks, and I'm going to react with each one 5 centimeters of magnesium ribbon. So they're going to be my control variables, the length of the magnesium ribbon and the volume of the hydrochloric acid. But what I'm changing, the independent variable, is the temperature. This one is at room temperature, which is 22 degrees, and this one I've gently heated with the Bunsen burner. Now, when I react them together, I'm going to use a gas syringe to measure the volume of gas given off in a set time, so that's going to be my dependent variable. This is the acid that's been warmed up. It's currently at 66 degrees, so I'm going to add the magnesium and start the stopwatch and measure the volume of gas given off in a certain time. So after 20 seconds, we can now read off the volume of gas. And that's produced 40 centimetres cubed of gas in 20 seconds. I'm now going to repeat the experiment with the acid that's at room temperature, which is 22 degrees. So the magnesium's going in. Start the stopwatch for 20 seconds. This time the reaction's made 9 centimetres cubed of gas in 20 seconds. We can now use the equation to work out the rate of reaction at the two different temperatures. So remember, the rate of reaction is the amount of product made divided by time, in this case the volume of gas divided by time. So at 22 degrees we made 9 centimetres cubed of gas in 20 seconds, so 9 divided by 20 is 0.45, and the units are going to be centimetres cubed / seconds, so centimetres cubed per second. And at the higher temperature we made 40 centimetres cubed of gas divided by 20 seconds, the time, and that is 2 centimetres cubed per second. So we can see at the higher temperature we've got a faster reaction, or in other words a higher rate of reaction. We're now going to see why that would be by explaining it in terms of collision theory. When I heated up the acid, the increase in temperature gave the particles more energy. That meant they were moving around a lot quicker, so there was more frequent collisions, and there was also more successful collisions because more of the reactant particles had the required activation energy. So more frequent collisions and more successful collisions mean a higher rate of reaction at the higher temperature. The opposite is true for the lower temperature. At the lower temperature, the particles would have less energy. That would mean there would be less frequent collisions, there'd be less successful collisions, and therefore a lower rate of reaction. And make sure you remember these explanations. I'm going to show you the effect of surface area on the rate of reaction by reacting these marble chips with hydrochloric acid. I've weighed out 20 grams each of small marble chips and some large pieces, but each one is 20 grams in total. As you can see, I'm carrying it out on top of a balance because this reaction gives off a gas, so the mass should decrease as it reacts. And the starting mass for all of the reactants and the equipment is 226.94 grams. I'm now going to mix the reactants together by pouring the acid onto the marble chips, and I'll start the stopwatch and I'm going to time it for 20 seconds to find out the decrease in mass after 20 seconds. And after 20 seconds, the mass has gone down to 226.54 grams, and it's still decreasing now. I'm now going to repeat the experiment with the large marble chips, and the starting mass this time is 227.69 grams. I'm going to add the acid to the marble chips and start the stopwatch for another 20 seconds. And this time the mass has only dropped to 227.68 grams. I then put the results into this results table, both the starting mass and the mass after 20 seconds for the small and large marble chips. I then calculated the loss in mass by subtracting one from the other, and that loss in mass is the same as the mass of gas given off. Now, to work out the rate of reaction, I had to remember the equation. The rate of reaction is the amount produced divided by time. So in this case, the amount of gas given off in grams divided by 20 seconds. So 0.4 grams divided by 20 seconds gave me a rate of reaction of 0.02 for the small marble chips, and 0.01 grams divided by 20 seconds gave me a rate of reaction of 0.0005 for the large marble chips. So we can see the small marble chips had a much higher rate of reaction. The reaction was going a lot quicker. We're now going to see why that might be by talking about collision theory. First of all, we need to understand what happens to the surface area of an object if it's cut into smaller pieces. So let's first of all imagine one big piece of a solid chemical, and that's a cube that is 10 centimeters by 10 centimeters by 10 centimeters. Well, to work out the total surface area of this one cube, we would find the area of one side, which is 10 by 10, so that's 100 centimeters squared. And then the total surface area of the cube, because it's got 6 sides, would be 6 times 100, which is 600 centimeters squared. Now, if we had the same volume of the chemical, but just chopped it into 8 smaller pieces, and each of those smaller pieces would be 5 centimeters by 5 centimeters by 5 centimeters, then we can see the area of one side is 25 centimeters squared. The area of one small cube is 150 centimeters squared, but the total surface area of all 8 cubes when added together is 1200 centimeters squared. So the point we're making with this is if you have the same amount of a chemical, but you simply chop it into smaller pieces, the combined surface area of all those pieces is much bigger than when it was together in one big lump. The way that affects the rate of reaction is that smaller pieces have a higher rate of reaction because they've got a larger surface area, so there are more frequent collisions in the same time. Larger pieces have a lower rate of reaction because they have a smaller surface area, so there are less frequent collisions in a set time. And make sure you remember this explanation in case you get asked about surface area on your GCSE exam. We're now going to look at the final factor that can affect the rate of reaction, and that is a catalyst. Now, for your exam, you need to remember the definition of a catalyst, and that is a catalyst is a substance that can speed up a chemical reaction but remain unchanged at the end of the reaction. And it's that last bit that people often forget for the second mark. Now, I'm going to show you a catalyst in action by looking at the reaction of hydrogen peroxide. Hydrogen peroxide naturally breaks down or decomposes, this is called a decomposition reaction, to form water and oxygen. And that would happen anyway, but the catalyst will just speed up the reaction. And because we're producing a gas, I'm going to use the upturned measuring cylinder to measure the rate of reaction. The catalyst I'm going to use for this is a substance called manganese dioxide. And the thing about catalysts is they are specific. So whilst this should be a good catalyst to speed up this reaction, you'd need a different catalyst to speed up a different reaction. The other thing about catalysts is you only need to use them in small amounts. So I've just got the end of a spatula here of manganese dioxide that I'm going to then add to the hydrogen peroxide. So I'll pop that in there now, start the stopwatch, and I'm going to time it for 20 seconds, and we can see that there's gas bubbling through already, and I'm collecting the volume of gas in that upturned measuring cylinder. Then after 20 seconds I can take the bung out, and now I can measure the volume of gas produced by the reaction. The reactions produced 26 centimeters cubed of gas in 20 seconds, so in order to work out the mean rate of reaction, I would do the amount produced divided by time, so that would be 26 divided by 20. But the reason I'm showing you this reaction is you can see just how much quicker the gas was given off when I added that catalyst. So how do catalysts actually work? How do they speed up the chemical reaction? Well, they lower the activation energy. So even the particles that are moving around more slowly with less energy, they then have enough energy to cause a reaction and cause a successful collision. And catalysts do that by providing a different pathway for the reaction. A common GCSE exam question is they will show you a reaction profile. In this case it's for an exothermic reaction. We can tell that because the energy level of the products is lower than the energy level of the reactants. And the question would be, draw on the energy profile the line for the reaction if carried out with a catalyst. And the key thing you need to remember is that catalysts lower the activation energy. Well, the activation energy would be from here to here. So we need to draw a line that is lower. So I'm going to draw it on now in red for with the catalyst, and we can see we've got a lower activation energy, which would be this bit here, but it starts and finishes at the same point. The required practical for this topic is talking about an experiment you could use to investigate how concentration affects the rate of reaction. In this required practical, you're expected to come up with a hypothesis based on collision theory. So your hypothesis could go something like this. If you use less concentrated reactants, the particles are less crowded, or there's less particles in the same volume, and therefore there'll be less frequent collisions and a lower rate of reaction. If you use more concentrated reactants, there's more particles in the same volume, or you could say there's more crowded particles, therefore there would be more frequent collisions and a higher rate of reaction. The examiners expect you to be able to describe a reaction either that produces a gas, and therefore you'd measure the volume of a gas, for example using a gas syringe, or a reaction that turns cloudy over time because a solid is produced. So I'm going to show you two methods that you could talk about for this required practical. These are the different concentrations of hydrochloric acid that I'm going to use, ranging from 0.25 moles per dm cubed up to 1 mole per dm cubed. So that is going to be the independent variable, as it's the thing I'm going to change. So I'm going to start off with the first concentration of hydrochloric acid, and I've measured out 50 centimeters cubed using a measuring cylinder. It's important in an exam question you state the quantities of each reactant and how you're going to measure them. I'm then going to add that to a conical flask, and I've already weighed out 0.5 grams of magnesium using a balance. So two of the control variables are the volume of acid each time is going to be 50 centimeters cubed, and the mass of magnesium each time is going to be 0.5 grams. So I'll add that second reactant now, and then very quickly replace the bung in the flask, and at the same time start the stopwatch. And I'm going to measure the volume of gas made after 20 seconds. Stop the stopwatch, take the bung out. I can now read off the volume of gas produced after 20 seconds, and I can convert that to a rate of reaction by doing the volume of gas produced divided by the time. I would then repeat that 2 more times for the first concentration of acid, discard any anomalous results, and calculate a mean for the 0.25 moles per dm cubed acid. I would then repeat the whole practical for the different concentrations of hydrochloric acid. You could also be asked about the method that uses the disappearing cross method. This is where a precipitate is made, which is a solid made when we react two liquids together. So once again we're going to mention the quantities of the reactants and how we've measured them using a measuring cylinder. So I would start off by saying I've measured out 50 centimeters cubed of sodium thiosulfate using a measuring cylinder and pour it into a conical flask. Then using a separate clean measuring cylinder so the reactants don't start to react together, I've measured out 50 centimeters cubed of the first concentration of hydrochloric acid, which is 0.25 moles per dm cubed. I'm then going to add that to the conical flask, start the stopwatch, and time how long it takes to go cloudy, so much so that I can't see the cross through the reactants. I'll speed up the film so that we don't have to wait too long. Now that I can't see the cross through the reactants, I stop the stopwatch. We then repeat that 2 more times for the first concentration of hydrochloric acid, we discard any anomalous results and calculate a mean from those first 3 results. We then repeat the whole thing with the other concentrations of hydrochloric acid. The last part of the rates of reaction topic is all about reversible reactions, and I'm going to show you a reversible reaction now by heating up this blue copper sulfate. This will need heating for a few minutes, so I'll leave it going and then I'll speed up the video so you can see the effects of heat on this blue copper sulfate. Notice how it's producing steam, and also there's some condensation on the cooler part of the test tube. The blue copper sulfate has turned into a white form of copper sulfate. This is the reaction we've just seen. I started off with hydrated copper sulfate, which means it's attached to water molecules. That was the blue form. And by heating it up, it changed into anhydrous copper sulfate. That means without water, and that was the white form of copper sulfate. The water molecules that are detached from the copper sulfate left the test tube as steam, and some of it condensed on the cooler part of the test tube to form condensation. But that's not the end of the story, because this is a reversible reaction. Let's see what happens if I add a few drops of water to the anhydrous copper sulfate. We can see it's changing back into the blue hydrated copper sulfate because it's a reversible reaction. A reversible reaction then is one where the products can change back into the reactants. And the way we show that on the equation is we use a special arrow that has half an arrow pointing forwards and half an arrow pointing backwards to show that once the reactants have changed into products, they can change back into the reactants again. And one thing I should mention was to get this reaction to work in the forwards direction, I had to heat it up with the Bunsen burner, so that means it was endothermic going in the forward direction. When I added the water back to it and got it to change back again, it would have given out some heat energy and been exothermic. So with reversible reactions, if they're endothermic in the forward direction, they're exothermic in the reverse direction. If they're exothermic going forwards, they're endothermic in the reverse direction. This reaction can actually be used as a test for water. If you suspect a liquid might be water, and you start with anhydrous copper sulfate, the white version, add the water to it, and if it changes back into the blue hydrated copper sulfate, then you know it's water that you've got. Another reversible reaction that can be used to test for the presence of water is cobalt chloride. I've got some cobalt chloride paper here which starts off blue, and if I add water to it, it changes to a pink colour. And we can change it back to blue again by drying it out in a desiccator like this. So if it goes from blue to pink, we know we've got water. Here's the equation for the reaction we've just seen. So we started out with the blue anhydrous cobalt chloride. It reacted with water to form the pink hydrated cobalt chloride. And we can get the reactants back again by drying it out in a desiccator, so that pink hydrated cobalt chloride changes back into the anhydrous blue cobalt chloride. We're now going to take a look at equilibrium and Le Chatelier's principle. A closed system is when the reaction takes place in a sealed container so that the reactants or products can't enter or leave the system. So imagine you've put a couple of reactants together in a conical flask and you've sealed it closed with a rubber bung. Equilibrium is the point where the forwards and reverse reaction are occurring at the same rate. And make sure you learn these two definitions for your exam. It's sometimes called a dynamic equilibrium because although the overall amount of products and reactants may appear to stay the same, the forward and reverse reaction are still happening. It's just that they're happening at the same rate. So it might look like you're not making any more of the product. You actually are. It's just that it's turning back into the reactants as quickly as it's being formed. The rest of this video is higher tier only. In fact, questions about this are aimed at the grade 8 and 9 students, so they tend to appear towards the end of the exam paper. So if you're finding it a bit tricky, that's okay, it's meant to be challenging. Just watch the video a second or third time until you understand more of it. So the position of the equilibrium can change. If the equilibrium shifts to the right, more products will be made. If the equilibrium shifts to the left, more reactants will be made. And the position of the equilibrium can be affected by the conditions of the reaction, such as the temperature, the pressure if the reactants are gases, or the concentration of the reactants or the products. Le Chatelier's principle can be used to predict what would happen if you change the conditions of a reversible reaction. And Le Chatelier's principle states that if you change the conditions of a reversible reaction in a closed system, the position of the equilibrium will change to try and counteract it. So whatever you do to the reaction, it will try and undo that change. For example, if you increase the temperature of the system, the equilibrium will change to try and reduce the temperature back down again. If you increase the pressure, the equilibrium will change to try and reduce the pressure back down again. Let's take a look at the effect of changing the temperature. So we can see in this reaction that the forwards reaction is exothermic and the reverse reaction is endothermic. So what happens to the yield of N2O4 if the temperature is increased? Now by yield we mean how much of it is made. Well, it will encourage the reverse reaction because the reverse reaction is the one that cools everything back down again. So if we increase the temperature, according to Le Chatelier's principle, it's going to try and reduce the temperature again, and the endothermic reaction will do that. That means the equilibrium position shifts to the left and less N2O4 is made. And this is a good writing frame for answering these questions. You say, is it going to encourage the forwards or reverse reaction? Will the equilibrium position shift to the left or the right? Therefore, will more or less of the product be made? Keep watching until the end because I'm going to put a link up to another video where I walk you through an exam question to consolidate your understanding of this difficult topic. So what would be the effect of changing the concentration? What happens to the yield of BiOCl if the concentration of BiCl3 is increased? Well, it will encourage the forwards reaction because by doing that, it will reduce down again the concentration of BiCl3. So it will try and undo the change we've put onto the system. So if it encourages the forward reaction, the equilibrium shifts to the right, and more BiOCl is made. So once again, we've set it out in terms of, will it encourage the forward or reverse reaction? Does the equilibrium shift left or right? And does it make more or less product? Let's take a look now at the effect of changing the pressure. What would be the effect of increasing the pressure on the yield of NH3? Well, first we need to look at how many molecules of reactants are on the left and how many molecules of product are on the right. And we can see on the left we've got 1 molecule of N2, 3 molecules of H2, so that's 4 molecules of gas on the left. On the right we've just got 2 molecules of NH3. So if we increase the pressure, it encourages the forward reaction as there are less molecules on the right hand side. So that will tend to reduce the pressure back again. If we're increasing and encouraging the forward reaction, then the equilibrium shifts to the right. And that means that more NH3 will be made. So don't forget to check out that exam question video. Thanks for watching.